Alright guys, so this is going to be a short video on tension. So this is a very basic problem. So um, right now we're finding T1, this is T1, and T basically just means the force of tension, the tensional force. So what is the force that this string has with this object? Well, we can kind of just think about it. So say that there's my fingers are a string and it's dangling this 10 kilogram mass, right? Like shown in the image. And then I'm just holding it. I'm not pulling it. No pulling, pushing. Just holding it. This thing is dangling straight. These fingers are not actually doing anything, not applying any force or any tension to the pen itself if it's just dangling. So this T1 is actually just 0. That's it. Let's go to a more complex problem. So in this problem, now it's still dangling, but we're dangling two masses and there's strings connecting them to the ceiling and to each other. So we have a 5 kilogram and a 10 kilogram. So what we have here is essentially tension is equal to the weight when it's just hanging down or if it's just dangling. So, and we know that weight is equal to F of G, which is equal to mg. So tension 1 only holds the weight of this 10. So it's literally just 10 times the 9.8. The tensional force always goes up and the weight always goes down, right? So so we're finding tensional force. So tension, right, T is going to just be equal to, or T1 is going to be equal to 98 newtons upward. That's the tensional force for this guy right here. Now we need to find tension force of 2. So this tension force is not just going to be 5 times 9.8. It's a little bit more complex. Just think a little bit. This T2 also has the strain of holding T1, the 10 kilograms, essentially. So basically, we just add these masses, and it's going to be 15 times 9.8, which comes out to be 147 newtons. So T2 is equal to 147 newtons, and that's it. Very simple. I promise the next one's going to be more complex. Alright, so in this question, we are to find the mass. So we see that the angles are equal to 5 degrees, and that the tension of this left rope right here is 4,500 newtons. So it's 4,500 newtons to the ceiling, and because this is 5 degrees and these are symmetrical, and this is also 5 degrees, then we can just know that this is 4,500 newtons as well, right? And that's why this box is in the middle perfectly still. So now this box is weighing this string downward. So that is our weights or force of gravity, whatever you want to call it, which we're trying to find mass is negative 9.8, right? The acceleration of gravity times mass. So in this question, there's always going to be an X tension and a Y tension. And TR is going to have an X tension and a Y tension. So what does that mean? That means that the up tension of the left and right combined is going to be equal to F of G, except F of G is just going to be the opposite direction, negative, right? So we're trying to find the upward tension so we can find the downward weight. So 4,500 is, so essentially this is the shape, and this 4,500 is the hypotenuse, and the 5 degrees is right here. So we need to find this right here. So the tension of the y. So tension of y is equal to, it's the opposite. Y is the opposite. So it's sine of 5 times sine of 5 is equal to opposite over hypotenuse. So we just multiply the 4,500 on both sides. So the tension upward is equal to sine of 5 times 4,500. But that's only for one side. So this upward tension is 392.2 newtons. But we also have that exact same thing going on the right. So let's just multiply that by 2. And that is going to equal to 784.4 newtons. So this is our tensional force in the upward direction. Our y component. And weight is our y component as well. It's just negative. So we're going to make it negative 784.4 is equal to negative 9.8 times our mass. Simply divide by the negative 9.8. Conveniently, the negatives are canceled out. And mass can be a safe positive number. And we will get basically 80 kilograms as our mass. And that's how we solve for mass. So the hardest part about this question is just understanding that these tensions are going at an angle, right, of 5 degrees. So we have to split it up into x and y components. If you can understand that, then it's very simple. As long as you know how to use trig, it's sine of 5 is equal to opposite over the hypotenuse, multiply the 4,500 on both sides. Then we get this. And another difficult part about understanding this question is why we're multiplying by 2 here. It's because we only solve for the left side. There is essentially these x tensions going out this way and up tensions both ways. So these are equal. That's why I just multiplied by 2. If I didn't know that they were equal, then I would have solved for the left, and then I also would have separately solved for the right. The reason why we know they're equal is because of the 5 degrees. And that's it. Next question. All right, so this is what's given to us in this problem, and we essentially need to find T1, T2, and T3. So the easiest one to solve for right here is going to be T3, and this is why. It gives us the weight, which is force of gravity. So this block here is going down by 250 newtons. So don't even bother solving for the mass. There's no point. It doesn't ask for it, and you don't need it. So force of gravity is equal to 250 newtons down. Well, this tension here, this tension 3, is going up, and it's opposing this downward force. Well, it gives us the downward force. So the upward force to oppose its falling or rise of the block, it's stationary here, is literally just the exact same number, except it's just a positive value, right? So this weight should technically be negative for directionality purposes, and for directionality purposes, this tension is going up, and it's just opposing the exact same amount of force, so it's just positive 250 newtons. Now, tension 1 and 2 are definitely a little bit harder, I'm sorry to say. So how are we going to go about these questions, about these portions? Well, we discussed in the last problem that there are x and y components. Okay, so this is very simple. This 25 is adjacent to x. This 50 is adjacent to x, but they're opposite of the y values. So essentially, T1 x is equal to T1 cosine of 50. Why is it T1 cosine of 50? Well, this is T1x right here. And that's the adjacent value. Cosine of 50 is adjacent over hypotenuse. So this is, it was T1x over T1 is equal to cosine 50. But I multiplied on both sides to get rid of that denominator, and so T1's on the right side now, is with multiplied by cosine 50. And so we can just do the same thing because now we understand the pattern where sine of 50 is just going to be opposite over hypotenuse. Hypotenuse is on the bottom again, so we multiply and bring it to this side. And it's sine of 50 because it's opposite instead of adjacent. And that is the y. And it's the same thing for the second tension, except for the fact that we're using tension 2. And it's cosine of 25, not 50. An easy mistake that you guys might make is that you actually keep using 50 by accident. Make sure you use the angles that you're supposed to use. So 25 for this side and 50 for that side. All right, so now let's just solve for cosine 50, sine 50, cosine 25, sine 25, and rewrite these bad boys. Okay, so now I boxed in what those cosine 50, sine 50, cosine 25, sine 25 are simplified to, and you can see the decimal answers, and we're still multiplying by the hypotenuse, T1 and T2. So that's all that changed. We simply simplified the expressions, and now let's see. T2 is going to the right, so that would mean that 0.906 of T2 minus, because T1 is going to the left, 0.643 T1 is going to be equal to 0. And our y's are both going upwards, so 0.766 T1 plus 0.423 T2 minus 250, because the weight is bringing them down, and that's going to make the y equal to 0 as well. So I'm going to erase this now so we can give ourselves some more space. And now it is simply time to just do some math. All right, so here's what we're going to do. We can just add on both sides this T1. So 0.906 T2. Add on both sides. So this becomes positive on this side. And that's it. Now let's isolate one. So we'll isolate T1 by dividing by the coefficient on both sides. So T1 is equal to 1.41 T2. So this is what T1 is equal to. But that's not your answer yet because we need to find T2. So I don't know if you guys noticed, but we're doing a system of equations in this problem. So now that we know what T1 is, we're going to put that into this T1 down here, okay? So let's rewrite this. 0.766 times T1, but we can just incorporate this 1.41 T2 plus 0.423 T2, and then add 250 on both sides is equal to 250. Now we just multiply 0.766 by 1.41 to simplify this T2. We'll add them together and then just solve for T2. So this becomes 1.079 T2 plus 0.423 T2 is equal to 250. Now we can add that onto each other. 1.5 essentially, T2 is equal to 250. So divide by 1.5 on both sides, and our T2 should be equal to 166.4 newtons. So that's T2. 166.4 newtons. Now, it's very simple. We just have to use this, right? So T1 is equal to 1.41 times T2, which is 166.4. So that's going to give us 234.4 0.64 newtons for T1. And those are our answers right there. So there we go. We have T1, T2, and T3. So essentially what we did in this problem is you need to find the X and Y components and using trigonometry. And then what you're going to do is you're going to set up a system of equations. And hopefully you already know how to use system of equations. And therefore you'll be able to solve for one variable, right? As we did, we replace. So make T1 is equal to this. And we replace T1 with T2. So we only have T2. We're able to find T2. And then we can put that back into the original problem to find T1. And you can do it the other way around too. And yeah, that is how you find all your variables. That's tension. See you in the next video.